welcome back. And today we're back out here in the garage with the beast itself because there's some pretty exciting work to do on here. In the previous episode, we took a really in-depth look at the diagnostic card itself, and I even went as far as making a schematic just by tracing it out by hand. And I'm like 98% sure that that schematic is correct, but that pales in comparison to the work that's been being done by the community for reverse engineering the code that is on the ROMs. It's humbling and amazing, and I don't know how to thank these people enough. Chris, Fire, 256 byte RAM, Peter, all of you have just done such an astonishing job. I'm at a loss for words for the amount of work that you guys have done for this machine. Thank you. Thank you so much. But I don't want to let you down because all of the work that you're doing is ultimately to get this machine up and running. And well, we think it's already pretty close, actually. In the couple episodes back, we probed the multiplexer card and we saw that it was putting out some data. And a couple eagle-eyed viewers, Peter most notably, started looking at the random shots of the scope that I was taking and figured out that the MUX card is trying to say error, and it's just not making it up to the terminal. So there's a couple things we need to tackle today, but ultimately the goal is to get error or something to display on the terminal. But that means that we need to figure out why the terminal wasn't working appropriately. And, well, also there's some work that I want to do on the computer itself down here. Talking with Fire and talking with Chris, who are reverse engineering the ROMs, they also started to take a look at the bootstrap ROM that is on the backplane. And, well, they've done unbelievably amazing work, but they were starting to think that the bootstrap ROM might make a little more sense if we knew exactly how the backplane was laid out. So I want to pull the backplane out and trace it out to get a full schematic for it, just like I did for the diag board. But also, I need to get the backplane out because the card edge connectors are incredibly stiff. I'm afraid I'm going to break a card every time I try to pull one out. I'll demonstrate for you. This is the printer card right here, and I'll try to... No, it's not going. It's stuck in there, and it hurts my finger just to try and get it out. So I need to get the backplane out and clean the card edge connectors a lot. It kind of work the cards in and out so that they can be plugged in and removed a lot easier, because right now something is going to break and that's bad news. So let's pull the cage out, get the backplane out, give it a good clean, trace it out, look at the schematic, look at the bootstrap ROM, the reverse engineering that's being done on that, and then once we have a clearer idea of what exactly is going on, we'll try to figure out what's going on with the terminal, and maybe we can get some communication between here and the terminal. So let's get started. All right, so check this out. This is the second MUX card, and I've only pulled this card out and put it in about 2 or 3 times since I've had the machine. And the card edge connectors are so stiff that when you have to install the card, you have to push on the edge of the card. But, well, there's no edge of the card here because you've got these DB9s in the way. So over the years, people have been pushing on the DB9s to get it installed. And, well, that's going to put a lot of stress on the pins, and the stiffer the connectors get, the more stress there is. And, well, I thought that there might be some broken solder joints along here, but I wasn't expecting it to be that bad. That's ridiculous. Every single solder joint on this second DB9 connector is just sheared and shattered, and each connector has at least 3 broken solder joints. Now, this board is a lot worse than the board that's in it that we were reading the error code off of, but either way, this is nasty. Those card edge connectors absolutely have to get a deep clean because this is just unacceptable. So let's get the cage out and get to work. Getting the computer cage out really isn't all that difficult. Actually, the hardest part is getting the cards out of the backplane. They're really, really stiff. But once I've got all the cards out, well, you can see that there's 9 cards in total. We'll set them someplace for safekeeping. And that's not actually on the workbench here. I just put them here temporarily because I thought it looked neat. But with all of the cards out of it and safely stowed away, all we have to do next is just remove the power supply connections on the back, and then it's just 4 screws holding the cage into the chassis. With those 4 screws removed, it slides right out the side with no drama at all. And then with it here on the bench, I need to get the backplane out of the cage to make it easier to clean the sockets, but also to make it so that I can beep out the entire backplane and figure out what the schematic for it is. The screws are not captive in either way, and neither are the nuts, so I have to actually hold the screw in place to remove the nut. But once you got them all done, the backplane actually slides right out the front of the cage with no problem whatsoever. Then, after spraying some contact cleaner into the card edge connectors, I took the backplane in and started the somewhat arduous process of beeping out every single line on here. And actually, it was pretty painless to trace out the backplane schematic. It really only took me about a day, whereas the diagnostic card took me the better part of a week, and something more complicated like the CPU 6 card, which is a multi-wire and I can't actually visually trace anything, would take probably months. So being able to knock it out in a day was fantastic. All right, I've got it all back together. I got the backplane back in the cage back in the chassis. I hooked the power supply back up to the backplane, and I have the minimum complement of cards in order to get this thing to boot. I have the CPU 6, the multiplexer card, and 1 memory card. Now there is a 4th card in here. It is the disk autoload card. I don't actually need it to boot. It's only in here for me to demonstrate how much easier it is to remove the cards now. I can do it with just one hand, and then the card is out with no problems whatsoever. Massive, massive improvement. So with just these 3 cards installed, the machine should post. Now, a lot of people mentioned that maybe the card order was important, and it is kind of. It's only important for the very first slot over here. Well, slot number 1 you can't actually put a card into, but slot number 2 is reserved for the CPU 6. And we can actually see that on the schematic, the wiring that goes to slot number 2 is different than the wiring that goes to the rest of the slots. But all of the slots from slot 4 on are identical. Now, I skipped slot 3 because it's actually blank on the backplane. You can't plug anything at all into slot 3. But the rest of the slots are the same, so it doesn't matter what card you plug into where. So I've just plugged in the multiplexer card and the memory card with a lot of space between them, so that way there's lots of airflow over them and I can get to them pretty easily. Now, in order to get the multiplexer to talk to the terminal, we got to figure out what's going on with the terminal. Now, in the previous videos, the one thing that got the absolute most comments out of anything was the terminal. But to address a couple of questions, the first thing that almost everybody commented on was that this terminal looked like it was current loop and not RS-232, and the MUX card was definitely putting out RS-232. And the reason everybody thought that is because it says EIA current loop here on the bottom. But it is actually a terminal that is capable of both current loop and RS-232. And you can see you can actually select between that with a simple dip switch flip over here. Now the dip switches is pretty much where the problem was. I just didn't have anything set up right. And I didn't have anything set up right for, well, 2 reasons. The first is that, stupidly, I was changing the dip switches without power cycling the machine. In hindsight, this seems completely obvious, but it didn't dawn on me while filming. So I need to turn the terminal off, set the dip switches to what I want, then turn the terminal back on. Most likely the terminal only probes the settings of the dip switches at power up, so when I was changing them while it was powered on, it was just confusing and compounding issues. The second problem, however, I am not going to take the blame for. I'm totally blaming it on ADDS. If we look closely at all of the writing on the back of the terminal here that tells me how to set the dip switches, they show it all as 0 as being down and 1 as being up. 1 is always on the top. In actuality, it's backwards. When you flip the dip switch, flipping it down is 1 and flipping it up is 0. This is absolutely ridiculous, and I didn't fully figure that out until I had managed to find the proper manual for it. And this isn't actually for this terminal. This terminal is an ADDS Regent Model 100. This is the manual for a Model 200, but they're pretty close to identical. The Model 100 doesn't have the auxiliary port here, and I think there's some firmware differences in them. And well, they actually say right here, each switch is a miniature rocker switch, which is pushed down for the 1 state or pushed up for the 0 state, which is exactly backwards of what is shown on all of the settings here. Well, I now know how to set up the dip switches. I'm going to get those set right. We will jumper across pins 2 and 3 with my little connector here, and then we will see if this thing is looping back properly. All right, so we've got the dip switches set to 9600 baud, full duplex, and a couple other settings. I actually went through and made a little dip switch list here to make sure that I got everything set correctly. And so every time I push a button now, it should transmit data out pin 2, which then goes through the jumper back into pin 3 and is received by the terminal, which should display it up here on the screen. So let's flip the power on and see what happens. All right, it took it a little time to warm up completely. It looks like we've got some junk printed up here. Let's see if we can clear that. Yeah, Control Erase still clears the screen. So let's type HELLO space WORLD exclamation point. Nice. Everything I type is being looped right back into the receive pin and is showing up here. And if I hit new line, it actually brings the cursor back to the new line instead of printing the character for new line. And if I hit line feed, it goes down to the next line. So there we go. The terminal is looping back perfectly with just a single jumper between pins 2 and 3. The terminal is set up to be as dumb as a dumb terminal can get. It doesn't need any handshaking lines at all. But what this means is that the terminal is actually receiving data and able to send data, so the computer should be able to transmit data into the terminal, have it displayed up here, and conversely we should be able to type something, have it sent into the computer, and have the computer do something with it. So let's plug in a cable and see what happens. All right, I've got my DB9 to DB25 serial cable over here. It's plugged into the back of the terminal and plugged into port 0 of our multiplexer card down here. It should be sending data to the terminal, so well, we'll go ahead and clear the screen here so that we've got nice clear view of what's going on up there. I'm going to have to pick the power switch again because I'm too lazy to splice in something else. Well, and it picks within like a second or two. So let's turn it on and see what happens. Nothing. Absolutely nothing happens. We aren't getting any data from there to there. But we know the terminal is actually receiving data because our loopback worked. And we know that the multiplexer card is actually sending something because we saw that on the scope. So I think the problem is steeped in our cable here. All right, so here's our cable. This is the DB9 side, this is the DB25 side. And despite the fact that you could have 25 pins populated, it's only using 4 pins. If I remember looking in the manual, about half of the pins are for RS-232, the other half are for current loop. Now, it's set up as a super dumb terminal. So pin 2 is transmitted data, pin 3 is received data, pin 4 is skipped, then pin 5 is CTS, which I believe is a clear to send signal, pin 6 is skipped, and finally pin 7 is ground. This is the cable that's supposed to go with it, but I started thinking maybe pin 2 and 3 here are not quite right. Maybe they're flipped or backwards or something. And well, I took the multiplexer card out and I started to beep out where each of the pins on the DB9 connector went to. We can see that pins 5 and 9 here have pull-ups to VCC, pin 1 goes to ground, and then we have, well, looks like we have 4 communication lines going on here. I'm not really sure what each one of these is meant to do, but we can see that the SN75154 here has 2 lines that go to pin 2 and pin 8, And then these SN75150s down here have two lines that go to pin 6 and to pin 9. Now an SN75154 is a line receiver, and the SN75150s are line drivers. So this is going to be transmit out, and this is going to be received data in. Well, let's beep them out and see what they're hooked up to. So I've got my alligator clip hooked up to pin 2 of the DB25, which should be transmitted data coming out of the terminal into the multiplexer card here. And so that should be going into the line receiver. And the line receiver is either pin 8 or pin 2. So let's check that right quick. So that should be pin 2. Nope. That should be pin 8. No, nothing on that. Okay. Well, maybe it's going into the transmit. That shouldn't be correct, but well, we'll check them just to be sure. That's pin 6 or pin 4. So we'll check pin 4. No, nothing on that one. And we'll check pin 6. Oh, look at that, it's beeping. All right, so I think we've identified our problem. Pin 6 is going into a line driver, and that's connected up to pin 2 of our terminal, which is transmitted data. So we have the terminal trying to transmit data, and we have the line driver trying to send data to the terminal, and they're just crashing into each other. It's not working. So neither of them is receiving anything. And I have a theory as to why this cable is set up that way. This is another cable that came with the system, and we can see that it's actually a Centurion made cable. It says Cent Comp Corp on it for Centurion Computer Corporation. And well, all the cables had these little tags on them that said 4-port on them. So I thought, yeah, absolutely, that's for the multiplexer card on the front, but it says 4-port to Minicom. And well, it's not actually a Minicom, it's a Micom, but that's talking about our little communicator modem here. This is a serial modem that I believe was used to hook up a bunch of different terminals. I haven't actually ever been able to get it to power on. Every time I plug it in, it's just totally dead. But I also don't think it's necessary for us to talk with that. But I think what's happening is that the serial cable that's supposed to come into this doesn't need to be reversed like it does if it's going directly to the terminal, because that's happening inside the Micom modem here. So all we need to do is flip pins 2 and 3 so that the transmitted data coming out of the terminal is going into the receive port of the multiplexer card. And we can actually do that with this DB9 RS232 breakout board because it has a dip switch in the middle that allows me to disconnect the connection from one side to the other. Now this is set up to display the standard that I believe IBM set well after this machine was built. So these pinouts here don't actually mean anything. So I actually went through and I measured what pins went to where on them. So we'll go ahead and flip all of the dip switches off to block everything. And then we want 2 of them to pass through. We want the CTS signal to pass through and the ground signal to pass through. And those are on 1 and 2 here. And then all we need to do is we need to flip pins 2 and 3 that go to the terminal, and that's going to be CTS and DSR according to here. Keep in mind that this is not correct, but because it's labeled like that, I can actually see where I need to put my jumpers here. All right, it's not pretty, but I've got the 2 signals switched that should be. So let's plug this into the MUX card and then plug our cable into this and into the terminal. And well, hopefully we can get it to boot. All right, we're all plugged in. The terminal is on and warmed up. Here we go, moment of truth. Fingers crossed. Yes, look at that. D equals. It's asking me to do something, and it came from the computer. Now D equals is asking me what drive I want to boot from, and well, from here I don't have a whole lot of options. Everything I type just says error, which I mean, that's understandable because it's expecting something very specific, and I didn't know what that was until we started looking through the bootstrap code, and it's looking to boot off of either the Phoenix drive, the Hawk drive, or a Finch drive and or floppy drive. And you select those by just pressing one character followed by a number. So Hawk would be H, Phoenix would be C because it's a CMD Phoenix drive, and Finch or floppy would be F. So if I type H, I don't get an error immediately. And then I need to type a number that tells it what platter to boot off of. So if I do H1, well, it gave me an error. Let's do H0, gave me another error. And well, honestly, that's not surprising. The Hawk drive is over on the bench with a very crashed head. But what is interesting is if I type C for the CMD drive, and then I push a number, it hangs. The whole thing hangs. So its interaction with the Hawk drive and its interaction with the Phoenix drive are very different. And the only way to get it out of this is to reset the machine by pushing the select button on the front, which brings us right back up here to the D equals prompt. Now to explain how mega this actually is, let's take a look at the bootstrap code. And I've got a printout of it here, and the static of the CRT is going to hold my piece of paper perfectly in place here, which is kind of nice. So the first instruction that we come across is a 1A02, and this is checking if a sense switch is set, and if it is set, we jump to LFC04. And if we look at FC04, that is a 718001 operation, which is a direct jump to the address of 8001. So if the sense switch is set, we jump straight out of the bootstrap code without ever getting to the rest of it. And there's a lot of bootstrap code left. So that's pretty interesting. And I think we're going to figure out exactly what that is when we get to the diag card. But the sense switch isn't set, so we go to the very next instruction, which is 7303, which is a jump to 3 bytes plus the program counter. So that essentially skips the next 3 bytes, the 718001. So we jump over that and we get to 80C5. And then we have a load and a store. We're loading in a specific value to set up the multiplexer terminal to 9600 8 in 1. And then once the terminal is set up, again, we load another value and we store that in a specific address. And this should send a signal to the terminal to clear the screen. Then we have 2 delay operations, and each of these delays is 4.5 milliseconds. And then we get to the prompt, a 901000. And again, we're loading up some values, we're moving it around, we're writing strings. All right, that's interesting. We call the write string operation, and the write string operation essentially goes into a loop until it sees the null terminator character. And what that's doing is it's essentially sending D equals / to the terminal. Then it returns right back to our next operation, which is 7B72, which calls the read character subroutine. So it goes down and it checks what character is being sent from the terminal back up to here. Once it's got a character, it then checks if that is equal to F, C, or H, and if it's not equal to any of those, it prints error. And well, that's just a small smattering of what's going on in the Bootstrap ROM, but we can see that it worked. It's doing computery things, so the CPU is fully functioning. The multiplexer card is working perfectly, and our RAM is not so broken that it's causing none of those other things to work. So yes, we have a fully booting Centurion computer. That is epic. But, well, without the drives, we can't do anything from here, unless we plug in the diagnostic board. If we plug in the diagnostic board, things should get very, very interesting. But you're going to have to wait until next week to see exactly what it is that I'm talking about, because in that episode, we're going to plug the diagnostic board in and start playing around with some genuine Centurion software. So I want to thank you guys so much for watching, and I hope to see you in 7 days.